Okay, so today we're doing the electromagnetic induction experiment. This one's a little different than most experiments we've done so far. One thing is that it has very few numbers in it. It's mostly qualitative, which doesn't make it easy, unfortunately. And it also depends a lot more on the theory that you've learned in class than maybe some experiments we've done. A lot of what we've done so far, maybe you could have winged it if you know something about circuits. This one, not so much. It's going to depend pretty heavily on the theory about magnetic and electrical fields and induced fields that you've gotten in class. Okay, and I'm going to review that just a little bit. Even though you've gotten it in class, it never hurts to hear it a little bit again, maybe in a different way. So when we're talking about when we're talking about magnetic fields and currents, okay, one can induce the other. I think you've learned that. One is not exactly the opposite of the other. If you have a electrical current and you're interested in what the direction of the magnetic field is that it induces, okay, that's pretty straightforward. You can use your right-hand rule on that, and you can just jump in and pretty well use it right away, okay? If the current is the thing that comes first, and the question is what direction is the induced magnetic field, that's where you can just jump in with right-hand rule right away, okay? Now, if the magnetic field is the thing that comes first, and you're being asked what's the direction of the induced current, it's a little bit more complicated. It's not exactly the opposite of the other. First, you have to ask, is the magnetic field changing? If it's constant, then that's the end of the problem. A constant magnetic field doesn't induce any current, and you're done. That's all there is to it. Okay. Now, if the magnetic field is changing, that's where you have to think about how it's changing. Okay. So what's going to happen when you have a changing magnetic field is there'll be another magnetic field that's induced. So now you've got two magnetic fields. So you've got a primary field and a induced field, or a final field or initial field and a final field, whatever you want to call it. Okay. And the induced field, or the secondary field, it will oppose the change in the primary field. Okay. That's the subtle point. It doesn't always oppose the field itself. Sometimes it does, but sometimes it doesn't. It opposes the change. Okay. So, and then you can apply right-hand rule to the induced field, not the primary field, but the induced field. So on the board right here, you're seeing an example. On the left there's a magnetic field pointed up, and it's increasing, okay? So since it's increasing, the induced field is going to point down, because if the first one is pointed up and increasing, the induced field wants to fight the change. And so in order to try to cancel out some of that increase, it will point the opposite direction in order to do that. Okay, it doesn't entirely succeed. It's never as strong as the primary field, but that's the direction. Okay, this experiment mostly concerns directions. So that determines that the secondary field is pointed down, and once you know that, then you can apply your right-hand rule to the secondary field, or the induced field, whichever you want to call it. Okay, and I don't know how well you can actually see it, but the current is going to be in loops around the induced field, and it'll point the way I've shown it on the board. Okay, where it's going into the board on the left and coming out of the board on the right. Okay. Now then, over there on the right, you'll see another example. Here's a primary field, B1. This time it's decreasing. It's still pointed up, but it's decreasing. Okay. This one's probably a little bit trickier. The induced field is actually going to point in the same direction. Okay. I think for a lot of folks, your first instinct might be to say it points opposite, but in this case, it does point the same direction because the primary field is decreasing. Therefore, the induced field points in the same direction because it's going to try to compensate for some of that decrease. It always opposes the change. It tries to undo the change. Okay, so that's why it points in the same direction as the primary field. And then you can apply a right-hand rule to the induced field. And so you'll see the way I've got it there is that it's going to be loops around the induced field, and it'll be entering the plane of the board there on the right and coming out on the left. Okay, so that direction around the induced field. Okay. Okay, now we're going to talk about equipment. Okay, the lab manual instructions are going to talk about coils, and they'll talk about inductors. Those two terms are kind of interchangeable. There's going to be several that you'll have. You'll have a couple of these small ones, which it calls Gilly coils. That's a name for them. So you'll have two of these small Gilly coils. So those can be inductors, but also you have this inductor, this big one that you saw last week in the oscilloscope experiment. Okay. When you get to it, we won't use it until part 3. Most of the time it'll be the small coils. But when you get to the last part where you use the big one, it'll have some kind of an iron rod in it, or maybe 2 or 3 rods that strengthen the inductance of it. So going back to the small coils, it's going to ask you to do things like, say, take a magnet. Here's a magnet. You'll have one of those. Notice one end of it's got a label on it. So let's say if you took the north end of the magnet, let's say that label is north, okay? That's the north end of the magnet. And you shove it into the coil, okay? So what's going to happen? What's the coil going to do? The coil, this side of the coil will act like a north pole in order to try to repel the permanent magnet that comes in, okay? So if a north magnet comes in, it's going to try to act like a north pole in order to push you away, all right? It always opposes. Now let's say the opposite of that. Let's say if we have a north pole of a magnet sitting in there at first, and we're going to pull it away, okay? In that case, this side of the coil would act like a south pole, because in order to undo what you did, in order to try to pull you back, this would have to act like a south pole, which means the other side acts like a north pole. So you could think of the coils having like a magnetic field through it where one side's south, one side's north, okay? So that's the deal on that. Let's see. And then there's a couple of conventions that we have to talk about. When we're talking about one of these coils, well, if it's got a magnetic field on it, if it's acting like a magnet, it's also going to have a current induced in the coil, and that could be either way. It could be clockwise or counterclockwise. But we're going to say, we're going to establish a convention that whenever we say clockwise or counterclockwise, that's with respect to looking at this side of the coil, the side that has the connectors on it. Okay, one side has connectors, the other doesn't. The other's just flat. So whenever we say clockwise or counterclockwise, that means that we're talking about as you're looking at this side of the coil. That way, when you say clockwise and your partner says clockwise, you know you're talking about the same thing. All right. So that's the deal on that. There's one procedure where it's going to have you put both of the coils together. All right. And you'll put them back to back, and where each coil has contacts on the outside. And you could talk about something like, say, a magnetic field that would be pushing through both of them. And even though it's one field, only one field, and it goes through both of them, it can be into this coil, but out of this coil. All right. So that's the way that'll work. Okay. Even though it's just one field, it's into this one, but out of that one. All right. So that's the deal on that. Other equipment, there's a switch, couple of switches. There's the knife blade switch like we've used before. You're going to use that in the first 2 parts of the experiment. And in the last part, you're going to use this other switch that's basically like a household switch like you see on a wall in a building. It works a little bit better for what we're doing in part 3, so that's why we have that. So anyway, 2 different switches. Depends on what part of the experiment you're doing. All right. And then we're also going to use the oscilloscope. All right. We're going to use it a little differently than we did last week in the oscilloscope experiment. In that experiment, the oscilloscope was set up in a mode where it just read in real time whatever voltage was coming into it continuously.
okay? So it was always in real time. Now, in this experiment, we're going to set it up where the oscilloscope can read one single event that takes place in time and just freezes it, okay? So you're going to have something, you're going to have a little circuit connected to it where you flip a switch, and you want to see what happens during that short period of time that includes while the switch is being flipped, while your current is going from off to on. Now, if you had it set up the way we did last week, it would just happen and it'd be over with and you wouldn't be able to observe it. But this is going to be in a different mode where it senses when something has changed. The oscilloscope senses when a voltage increases, and it'll take sort of a snapshot of it that lasts a few milliseconds and then just freezes it. Okay, so it's kind of like a pause on a DVD. So that way you can look at the event that happened and study it as much as you want. You can look at it all day if you want to. All right, even though the event is over with. All right, so that's pretty much everything, I think. Also the galvanometer, we're going to use that, but you've used it before. All right, so okay. I'll leave you to get to it.